We on Earth are exceptionally lucky. While we are very rarely conscious of it, we exist and are alive today because Earth has an oxygen-rich atmosphere that we are breathing right now. And not only that, but the atmosphere provides safety from the cruel environment of space. It's visually beautiful, and it gives us a place to grow, play, and develop. Let me start by showing you some of these remarkable videos. If I were to ask you where Earth's atmosphere is, I think most people would quite confidently say it was all in this area here. Surprisingly, this is not actually the case. This video was taken on the ISS, or the International Space Station, which orbits the Earth at a distance of 340 kilometers. Earth's Exosphere, which, depending on who you talk to, is the final frontier of Earth's atmosphere, starts at roughly 500 kilometers and extends up to halfway to the Moon. The layers you are looking at in this video are in fact only the troposphere, stratosphere, and mesosphere. Beyond the mesosphere, but only barely visible, are the thermosphere and then the exosphere. But what is the difference between all these spheres? What do they actually do? Let's start right at the base layer, and the layer we are most familiar with because we live in it, the troposphere. At only 20 kilometers high at the equator, it's the thinnest of all the atmospheric layers. However, the troposphere is not a consistent height across the globe. The further towards the poles you go, the lower it reaches. At the mid-latitudes of the planet, it rises to 17 kilometers, and by the poles it's only 7 kilometers high during winter. Most commercial airlines in fact try to fly above the troposphere where possible, as they can avoid most weather disturbances in the stratosphere. But we'll get to that point later. The defining thing about the troposphere is that the higher you go, the colder it gets. And from my own personal experience of living in Switzerland, this can especially be seen when it's 20 degrees centigrade at the base of a mountain, but at the top it's still snow-capped. This disparity in temperatures is due to the way heat energy is transferred with conduction, convection, and radiation. Let's understand how this works. Firstly, heat is emitted from the sun in all forms of electromagnetic radiation. Most notable to us is light. This includes not just visible light, but infrared light and ultraviolet. Light is a simple energy, and this energy turns to heat when it impacts particles. Dark, non-glossy materials absorb this energy the best, which is why asphalt on a sunny day can reach temperatures of over 65 degrees centigrade. On the other hand, Earth's atmosphere is not as good at absorbing this energy, and most of the light passes straight through. But interestingly, the atmosphere does interact with some wavelengths of light, particularly blue wavelengths. This is a process called Rayleigh scattering. Gas molecules are smaller than a wave of light, so when a light wave hits one, you can only absorb some of it. All the different colors can be absorbed, but the higher frequency blue light is absorbed more often. After a while, the gas molecule radiates the same light it absorbed in a different direction. So when you're looking at the sky, what you're seeing is the blue from sunlight being scattered by a gas particle exactly in your direction. This is why the sky appears blue. Due to the atmosphere's poor absorption of solar energy, the atmosphere is not heated very much by the sun itself, but rather through the two other processes of heat transfer, conduction and convection. Solids are much more densely packed than gases, and so are much better at absorbing the sun's light. Because of this, the ground is warmed easily by the sun. Light colors and glossy materials are not good at absorbing light, and will often reflect it back. Snow, for instance, does this. Dark, matte materials absorb a lot more of this solar energy and then release the heat back into the atmosphere through conduction. Conduction is the process of a particle being heated and then releasing this energy by exciting the particles next to it. An easy way to imagine this is a pot of water on a stove. The hot pot conducts the heat to the water particles around the edge of the pot, which then heat the water particles next to them, and so on. This process of conduction is why cities are often hotter than rural locations. My capital city of London is often a few degrees warmer than the UK average on a consistent basis because the tarmac and concrete from the streets and buildings absorb, then release the sun's heat easily into the nearby atmospheric gas particles. But this happens to some degree or another across the whole world. A surface absorbs the heat of the sun and then releases it through conduction into the surface atmosphere. When gas particles are heated, they move further apart from one another, expanding and increasing in volume. This is where convection comes into play. Because the volume of the gas is increasing, but the amount of particles stay the same, its density decreases, and so the gas rises. As it rises, air pressure decreases, and the gas particles spread out even further. Individual particles begin to lose their heat energy through radiation. Eventually, the surrounding temperature is equal to the gas particle itself, and it can no longer rise. Instead, the particles start dispersing sideways. As the heat is further expended, the gas becomes cooler and denser and starts to sink again. This process happens on a grand scale near the equator and explains why the troposphere is higher near there. The equator is exposed to the most sunlight, and so when the air is heated near the surface, it rises very high. Following the process of convection, it reaches the point of no longer being hotter than the surrounding air, moves sideways, cools, and then drops again. Once at the surface, it fills the gap created by more rising air near the equator, creating this circle. This is called the Hadley cell, and similar cells can be found around the mid-latitudes and the polar regions, just to smaller extents. Because of these cells, gases from the stratosphere and the troposphere do not often mix. These cells are also the cause of trade winds, tropical rain belts and hurricanes, subtropical deserts, and the jet streams. Interestingly, because the cooled air is descending around the 30-degree latitudes, and at this point it's lost much of its heavier and denser humidity, precipitation will be much less common in these parts of the world where the dry air descends. Looking at an average rainfall throughout the year, it becomes very apparent that the Hadley cells have a big impact on the weather of this planet. 75% of the total atmospheric mass of Earth can be found in the troposphere. Its composition is mostly uniform throughout the planet, being a mix of 78% nitrogen, 20% oxygen, and small amounts of other gases. The exception to this uniformity is unsurprisingly water vapor, which is affected by the water cycle. We notice the presence of water vapor in two ways: humidity and clouds. In the form of humidity, we can't see the water vapor, but can rather feel it. Water vapor we can see comes in the form of clouds. In the atmosphere, there are very small particles of dust and salt known as aerosols. They are much larger than water vapor particles and provide a surface for the water vapor to condense onto when the vapor rises and cools. When enough water vapor particles condense onto the aerosol, a cloud droplet is formed. These droplets are so small that 1 meter square can contain 100 million of them. When there are enough droplets, a cloud becomes visible. As the cloud becomes saturated with cloud droplets, they can merge and eventually fall from the sky into the form of a raindrop. There are many different types of clouds, and they are formed in slightly different ways, but this basic explanation will suffice for this video. As I mentioned, temperature in the troposphere decreases with height at a rate of about 6.5 degrees centigrade every 1 kilometer. Also decreasing in height is air pressure. Dividing the troposphere from the next atmospheric layer, the stratosphere, is something called the tropopause, defined as the point air temperature stops decreasing the higher you go. In fact, just above the tropopause and going into the stratosphere, it starts to get hotter again. This is because of a layer in the stratosphere that is better at absorbing solar radiation, thus warm in the stratosphere, and that is the ozone layer. Ozone is 3 oxygen atoms combined into 1 molecule, or O3. Down in the troposphere, the oxygen we breathe is actually dioxygen, or O2. It is very beneficial in the stratosphere, as it absorbs a lot of dangerous UV light before it reaches us on the ground. The concentration of ozone in the ozone layer is actually only about 10 parts in a million, but that is enough to protect us. Ozone is formed by UV light split a normal O2 molecule into 2 oxygen atoms. One of these atoms then combines with some unbroken O2 to form O3. UV light then breaks up the O3 molecule back into O2 and an oxygen atom, and this cycle continues constantly. The stratosphere contains 20% of the mass of the atmosphere. It's for the stratosphere because it is stratified in temperature, with warmer layers higher and cooler layers closer to the Earth. The ozone increases in the temperature the higher you go. At the equator, the stratosphere starts at 20 kilometers and ends at 50 kilometers. There's not much in the way of convection in the stratosphere, the only temporary exceptions being caused by huge storms or volcanic eruption pillars. When air moves in the stratosphere, it is more often horizontally than vertically. This is why commercial airlines prefer to fly in the stratosphere where possible. There are rarely any clouds or weather, and the air isn't moving about as much. Interestingly, you may have heard of the world record skydiving jump performed by Felix Baumgartner. He jumped from the height of roughly 39 kilometers, which is still well within the limits of the stratosphere. Clouds very rarely form in the stratosphere as the air is so dry. Very occasionally, however, around the poles, nacreous clouds can form. Sometimes nacreous clouds come made of water, but rather other substances such as nitric acid. When seen just before dawn or dusk, these clouds are beautiful as they glow brightly with vivid iridescent colors. Because of the curvature of the Earth, the sun shines on them from below to provide this effect. After the stratosphere is the middle atmospheric layer, the mesosphere. Between these two layers is the stratopause, the region where the air temperature stops increasing and starts decreasing again. At this point, the air pressure is only 1/1000th of what you would find on the surface. The mesosphere starts at 50 kilometers and ends at roughly 100 kilometers. Towards the top of this layer can be found the coldest places on Earth, where the temperature can drop as low as minus 143 degrees centigrade. Again, there can be very rare type of cloud found in the mesosphere. These are called noctilucent clouds, and they are again very beautiful. Found between 50 degrees and 70 degrees north and south of the equator, and around 76 to 85 kilometers up. They are the highest type of cloud found on Earth. Like the stratosphere's nacreous clouds, they can only be seen while the sun is below the horizon. They are a type of water ice cloud, the difference being they can form with or without collecting on dust particles and are sometimes purely water vapor clouds. The source of the water and dust, these high in the atmosphere, are not known with certainty, but could come from micrometeors or volcanic eruptions. Water vapor from rockets can also cause noctilucent clouds, most recently from the SpaceX rocket Falcon 9. They're really spectacular, especially when you consider how high they are. This is a view from the perspective of the International Space Station. Even in this image, you can visibly see the different atmospheric layers, the troposphere, stratosphere, and mesosphere. Interestingly, the mesosphere is the least understood of all the atmospheric layers, even referred to as the ignorosphere, as it's above the flight capabilities of aircraft and below the minimum safe orbit of satellites due to atmospheric drag. The only times measurements can be taken are by rockets, and only for a few minutes as they ascend to the thermosphere, the next atmospheric level. As you might have guessed by now, above the mesosphere at roughly 100 kilometers is the mesopause. And as you might have guessed again, the mesopause is the point where the temperature stops decreasing and starts increasing again throughout the thermosphere. In fact, temperature can get extremely hot in the thermosphere depending on the solar activity, as much as 2,000 degrees. Although it's so hot here, because of the exceptionally low air pressure at this point, there are not enough gas particles to transfer much heat, so it would still feel well below 0 degrees. To give you an idea of how little gas there is here, above 160 kilometers, molecular interactions are so low that sound cannot travel anymore. The thermosphere is the thickest of all the atmospheric layers, rising from 100 kilometers all the way to 600 kilometers, but it only contains 0.002% of Earth's atmospheric mass. The thermosphere is actually considered by a lot of people to be the start of space. Satellites, and even the International Space Station, orbit within the thermosphere. But that's also why many satellites' orbits degrade, eventually with them burning up in the lower parts of Earth's atmosphere, because they were never really in true space, and atmospheric drag was still slowing them down enough that they eventually fell out of orbit. The thermosphere also serves an important purpose to us on Earth. A lot of the most dangerous and highest energy electromagnetic waves from the sun are absorbed in the thermosphere, and the effects of this can be seen as beautiful aurora in the sky. These high-energy waves interact with particles high in the thermosphere, exciting them and making them glow in many different colors, the most common on Earth being green. Above the thermosphere is the thermopause, which can range in height from 500 kilometers to 1,000 kilometers, depending on the time of day, the amount of solar activity, and a host of other factors. Above the thermopause is the last atmospheric layer, the exosphere. In the exosphere, there are very light gas particles like hydrogen present. However, due to the distance between these particles, they don't act as a gas, as they do not collide with other gas particles. They are, however, still gravitationally bound to the Earth. Near the thermopause is where this gas stops behaving a gas due to lack of collisions. And at the top of the exosphere, reaching from 10,000 kilometers to halfway to the moon, is where the sun's radiation pressure on these gas particles overcomes the gravity of the Earth. We are now in true interplanetary space.